This is part 2 of the AP Stats summer assignment, and in this video, we're going to cover some material that's a bit more complicated than what we covered in part 1. AP Stats is difficult. I don't expect you to understand all of this, especially without having me there to help and answer your questions. It's more about just getting those building blocks out of the way so we can start doing some problems and not have to cover all the terminology. In that first video, we talked about describing a distribution using SOX, where the letters in SOX stood for shape, outliers, center, and spread. We're going to start with center, and when we talk about a measure of center, we're talking about describing an entire distribution with a single typical value. So if we want to take a whole data set and summarize it with just one number, what would we use? The three obvious ones are the mean, median, and mode, and you've probably seen all three of these terms before. Another word for the mean is just the average, and we find the average by adding up the entire set of numbers and dividing by however many there are. That's what this equation is saying right here. When you see this fancy looking E right here, this is the Greek letter sigma. That means we're adding up everything in this variable. So this variable would have a data set of a whole bunch of numbers. We add them all up. We divide by the sample size, which is what that N stands for on the bottom, and we get Y bar. When we have Y with that bar on the top of it like that, that just means that that's representing the average of that variable. So the pros of using the mean is that it's widely considered the best measure of center because it's calculated using every data value, which is not true of the median or the mode. Cons is that the mean can be pulled away from the center if there's outliers or if we have a skewed distribution. Next up, we have the median, which is the middle of the distribution. Make sure you put all the numbers in order first. As an added note, the median is not necessarily the middle number because sometimes there isn't a middle number. Like in this distribution, we have 8 data values, and if we cross off one in the front, one in the back, we end up with 2 in the middle. We average those 2 in the middle to get our median. Just note 14 isn't actually in this data set, and that's okay. Pros for median, it's easy to find, it's resistant to outliers. Unlike the mean is sensitive to outliers, meaning that an outlier is going to pull the mean away from the center. That won't happen with a median. Cons are it's less accurate because it's not using all the values in our data set. It doesn't use these numbers at all in calculating what the median is. Lastly, we have the mode, which is the most often occurring value. We can have multiple modes if more than one data value occurs the most, or no mode at all if all of them happen the same amount of times. We'll also often see our data displayed graphically, which means the mode is the peak of that distribution, and sometimes it's bimodal or multimodal, meaning that there's multiple peaks. Pros and cons, the mode is only used for categorical data. So if we're talking about eye color, we can say that most people have brown eyes, but for anything numerical, quantitative, we would want to either find the mean or the median. So that was center. Let's move on to spread. We have 2 distributions here. We have this one at the top and this one at the bottom. And we can see that they both have the same mean, median, and mode. It's 60 for both of these distributions. However, they're very different distributions. The one on top is tightly clustered around 60, and the one on the bottom is really spread out. And that's important information for us to know, and that's why we want to learn about these different measures of spread. The simplest measure of spread is the range. It's how far it is from the minimum to maximum value, and we're just going to subtract those 2 data points. As a note, the range is a single number, so we wouldn't want to say that the range of the quiz was from 70 to 100. We would say that the range of the quiz is 30. Pros are that it's very easy to find. Cons are that it's extremely sensitive to outliers. If we have a single outlier in the data, whether it's at the top or the bottom of the distribution, it's going to give a really distorted view of the data. Let's say somebody didn't take that quiz. Right now they have a 0. Now our range is 100 instead of 30. Next up is the interquartile range, often abbreviated IQR. This is a term you probably haven't heard before, and this is describing the middle 50% of the data. So we want to split our data up into quarters. So if we found the median to start, we've split it into halves, and then we take each half of the distribution and we split it in half again. That's going to give us our quartiles. So Q1 is our 25th percentile, Q3 is our 75th percentile. These are going to be data values in the actual distribution, and we're just going to subtract those 2 data values. that'll give us the IQR. One of the pros of using the IQR is that it ignores the extreme values. So if we have an outlier at the top, it's going to be cut off because we're stopping at the 75th percentile. Same thing with the bottom, stopping at the 25th percentile. Cons are that it's more difficult to find. We want to use the IQR to describe the spread of skewed distributions, and the IQR is always paired with the median as a measure of center. As an example here, we have a 10-number data set, and we're trying to find the quartiles, which will allow us to find the IQR. So in a 10-number data set, our sample size is 10. The median is going to be the average of these two middle numbers, because there's two of them, and we get a median of 80. That's our quartile 2. It's the 50th percentile. 50% of our data is below 80. 50% is above 80. Now let's find quartile 1. So quartile 1 is going to be the median of the first half of the distribution. Here we get quartile 1 equals 70. This is the 25th percentile. 25% of our data is at or below 70, and the other 75% is above it. Same thing with quartile 3. This is the 75th percentile, meaning there's 75% of the data at or below 90. The remaining 25% is above it. To find the IQR, we just take Q3, we subtract Q1, and we get an IQR of 20. Lastly, we have the standard deviation, which is probably a term that you've heard used before, but you don't really understand what it is. So a simple definition is that the standard deviation is the average distance from the mean for an entire data set. Here's the actual equation that we would use to calculate a standard deviation. The good news is that we're really never going to use that. We're going to use our graphing calculators, and that's just going to tell us what it is. So the pros of using the standard deviation is that it's calculated with every data value in the data set, just like the mean is. And because of that, we want to pair this one with the mean. So if we're giving the mean as the measure of center, we pair it with the standard deviation as the measure of spread, just like median and IQR go together. We want to use this for distributions that are approximately normal and unimodal, okay? Unlike a skewed distribution, which would have a tail to one side. Cons are it's sensitive to outliers. So if we have one outlier, say way out here, that's going to affect the standard deviation while it wouldn't affect the IQR. Now, one of the nice things is that when we're in class together, we're going to use our calculators to do all this math that we're talking about right now. So the explanations are more about understanding what it means when our calculator tells us that the IQR of a distribution is 7. So we'll put a whole data set into our calculator, we'll run a little program, and it's going to give us summary statistics, which is really just another way of saying important numbers that we would want to know, like the mean or the median or the range, etc. There's something called a 5-number summary. That includes the minimum, maximum, and all 3 quartiles. Remember, the median is quartile 2. And we can use that 5-number summary to make something called a box plot. There's 2 kinds of box plots. There's a regular box plot and a modified box plot, with the only difference being that modified box plots also display outliers while regular box plots do not. In the first video, we talked about outliers being data points that are far away from the other values, but we can actually identify outliers mathematically using 2 different methods. The first one is called the outlier rule. We're going to use the quartiles and the IQR to determine mathematically, is something an outlier? So if a data point is more than 1.5 IQRs away from the quartiles, it's identified as an outlier. So in other words, if we have quartile 1, and we subtract 1.5 times the IQR, anything that's lower than that value would be considered an outlier. Same thing on the upper side using quartile 3 and adding 1.5 times the IQR. So let's find the 5-number summary for this data set and use it to determine if there's any outliers. So if you want to get some practice finding quartiles, you can do that now, or you could just trust me when I tell you that this is what you'll get. This is the 5-number summary because it's giving you the minimum, the maximum, and the 3 quartiles. And we're going to use this to figure out, are there any outliers in this data set? So when we look at this, we would probably be inclined to say no, there are no outliers because all these numbers are pretty close together. There's not anything that's really far away from the other ones. But let's use this outlier rule. We're going to start with the lower fence. Take quartile 1, which is 3, and we subtract 1.5 times the IQR. Now to find the IQR, we're going to subtract Q3 minus Q1. So the IQR is 2. So take that first quartile, subtract 1.5 times that IQR, and we get 0. Anything less than 0 is an outlier, which means that this -1 on the left side is a low outlier. Now we want to do the same thing with an upper fence. This time we take quartile 3 and we add 1.5 times the IQR. We get 8. Anything above an 8 is an outlier, which means this 9 up here is an outlier. Now we can use this to make a modified box plot. So to start, we want to make a scale, and we want to make sure that the numbers on our scale are spaced evenly. I have them by 2s here. You don't have to have every number. If this was a large span of numbers here, we could go by 5s or 10s. Now we want to start off by drawing the box. Okay, and the box is going to be the quartiles. So we're going to go from 3 to 5 for our box, and the median is going to go right in the middle here. Now off of these, if this was a non-modified box plot, a regular box plot, we would just go from the edge of that box out to the lowest value, which is actually like here. But we're going to make a modified box plot, so we want to show outliers. So that -1 is the outlier, which means we want to go to the smallest value that's not an outlier. Okay, we're going to go from the edge out to a 1 there. Same thing on the high side. Largest value that's not an outlier is the 7. That's why this is going to about a 1. This is going to about a 7. Outliers are denoted by little symbols. So we have an outlier at -1. We would make like an asterisk or a dot at -1, and then another outlier at 9. A box plot tells us a lot about a distribution. So first, it gives us a measure of center. The median is the middle line in that box there. So even if we didn't have the data set, we would know that the median of that distribution was 4. Tells us the middle 50%. That's the IQR. Okay, that's how far apart the two edges of the box are. In this case, 2. Could tell us the shape. So when we look at that box, we could see that it's pretty much symmetrical. The whisker on the right side and whisker on the left side are about the same. Might have been a little longer on the right side. So if it's symmetrical, we could just say it's symmetric. If the whisker on the right side is longer, we would say it's skewed to the right. And obviously it tells us the outliers, which were those little asterisks on the edges. It doesn't show us any gaps in the data, which is why it's always helpful to view a box plot along with a histogram. So here are some examples. We can see that this distribution is approximately unimodal and symmetric. And if we look at this box plot, the whiskers are about symmetric as well. Over here, for example, we have a distribution that's skewed to the right. The whisker on the right is longer than the whisker on the left. Next up, we have z-scores, which tells us how far a data value is from the mean measured in standard deviations. It's given by this equation here. X is our actual data point. Greek letter mu is the mean of the distribution, and Greek letter sigma is the standard deviation. Z-scores are also called standardized values. They have no units, and once we have a z-score, we can compare it to any other z-score, even if we have apples and oranges. A negative z-score tells us that the data value is below the mean, and a positive z-score tells us that that data value is above the mean. So for example, we have a college deciding between 2 students for one admission spot during the fall semester. Their applications are identical, with the exception that student A scored a 1380 on the SAT, and student B scored a 31 on the ACT. Which student should the college accept? So here we have 2 different test scores, but they're on different tests. So we're going to have to standardize these scores to see which of these students are actually more impressive. So we have their scores on each of these tests, but obviously that's not enough. First additional thing we have to know is the mean score on the ACT and SAT. So we have those 2 here. SAT is 1060, ACT is 21, and we notice that these scores are both significantly higher than those averages. So we still don't have enough information. The other thing that we need to know is the standard deviation. So standard deviation for the SAT is 195, ACT is 5.4, and now we can use all of these data values to find a z-score. So let's start with this SAT score. What's the z-score for an SAT score of 1380? So we're going to take that data value, we're going to subtract the mean, which it tells us is 1060, and divide by the standard deviation, which it tells us is 195. When we do that, we get 1.64. That z-score is telling us that this SAT score is 1.64 standard deviations above the mean. Positive z-scores are above the mean, meaning if this was a negative z-score, it would tell us that that data value is 1.64 standard deviations below the mean. Same thing with the ACT. This time we're just using this data value, subtract the mean of 21, divide by that standard deviation, we get 1.85. So this is more standard deviations above the mean than that SAT score was, meaning this student is the more impressive student. Okay, it's farther above the mean. So a z-score really tells us how unusual a data value is by telling us how far it is from the mean. If a data value is exactly equal to the mean, it would have a z-score of 0. Z-score of 1 means that that data value is exactly 1 standard deviation above the mean, -1 below the mean. There's no standard for large and small z-scores, but anything past 2 is typically considered unusual. So this is our second rule for determining outliers. If a data value has a z-score larger than 2 or smaller than -2, we consider that data value an outlier. Now, as a note, we only want to use z-scores for distributions that are symmetric and unimodal. We wouldn't want to find a z-score for a skewed distribution, because for a skewed distribution, we would use the median for the measure of center and not the mean. A distribution that's symmetric and unimodal is also known as something that's approximately normal. And that leads us into our next topic here, normal models. So anytime we see something like this, n parentheses, 2 numbers, that's telling us that we have a distribution that's unimodal and symmetric. It's taking that bell shape on with a mean of whatever came first, standard deviation of whatever came second. And the nice thing about normal models is that they always follow a very predictable pattern. So for example, if we move out 1 standard deviation above the mean and below the mean, about 68% of all our values are going to fall within that range, 1 standard deviation above and below the mean. If we move out a second standard deviation, 2 standard deviations above and below, that's going to cover about 95% of all values. And if we move out 3 standard deviations, at this point we've covered almost everything in our data set, 99.7%. This goes for any distribution which is approximately normal, and these distributions occur all around us all the time, just naturally. This is called the 68, 95, 99.7 rule, or more simply, the empirical rule. So here's a graphical representation of it. We have our mean in the center here. We're going to go 1 standard deviation above it, 1 standard deviation below it. 68% of all our data values are going to fall in that range. 95% are going to fall in the range that covers 2 standard deviations above and below, and then pretty much everything, 99.7%, fall within 3 standard deviations of the mean. Now we can use these numbers to solve problems. So let's say we're talking about the SAT math section, which has an overall mean of 500 and a standard deviation of 100. Question is, what percent of students score between a 400 and a 600 on the math section of the SAT? So 400 here, this is exactly 1 standard deviation below the mean, so that has a z-score of -1. 600 is exactly 1 standard deviation above the mean. Within 1 standard deviation of the mean, 68% of all students should score in that range. So let's take it a step further and say you scored a 600 on the SAT math section. What percent of students did better than you? So we had just talked about how 68% of the data falls within this range. That leaves 32% in both of these sections out here. So 32% left over, and that's from 100 minus that 68%. This curve is symmetric, which means whatever we have on this side, we also have on this side. And since there's 32% split across those 2 sides, that means each of these is 16%. So 16% of students score above a 600. What percent of students score between a 300 and a 500? So now we're talking about this section. So this 300 is on the range of 2 standard deviations. So 2 standard deviations below, 2 standard deviations above. If we want this whole range, that would be 95%. But we don't want the whole thing, we just want this side, which means it's going to be exactly half of that, and our answer would be 47.5%. Last thing to cover is how shifting and scaling data affects different measures of center and spread. So let's start with a simple data set. It's 10, 20, 30, 50. Here's the mean, median, range, standard deviation. If we shift this data set, mean we're going to add the same number to everything in the data set. In this case, it's 100. So now 10 becomes 110, 20 becomes 120, etc. We can see that the mean also increases by 100. Same thing with the median. So measures of center change with that shift. But let's talk about the spread. How far apart are they? Are they more far apart now that we've added that 100 to all those data points? So they were originally a range of 40. This is still a range of 40. That hasn't changed. They're not any more spread out over here than they are in the original distribution. So when we add a constant to every data value, it changes the measures of center, mean, median, mode, and measures of location, if we found the quartiles of both of these, or the minimum and maximum. All those change, but measures of spread do not change. Now let's talk about scaling data. So instead of adding something, we're going to multiply it. So this gets multiplied by 2, and same thing with all these other numbers. Again, measures of center also get multiplied by 2. But this time, the measures of spread change with it. So the range is now 80. They've gotten twice as far spread apart as they were originally. Standard deviation is also going to increase by a factor of 2. So for this last question, let's imagine we have a distribution of SAT verbal scores that have a mean of 450 and a standard deviation of 100. Part A, how would adding 50 points to each test score affect the mean? So if we added 50 to every data value in the data set, this mean is also going to increase by 50, and we'll get a new mean of 500. Standard deviation was 100. What would the new standard deviation be after adding 50 points? Stays the same. So they're not getting any more spread out when we add 50 points to every test taker in this distribution. Suppose we drew box plots of test taker scores a year before and a year after the recentering. How would the box plots differ? So whatever that original box plot looked like, let's say it looked like this. The new one, once we add 50, is just going to move to the right 50 units. So it's going to look the same. It's just the whole thing shifts over to the right 50.